Hello, everyone. Welcome back. So today we want to talk about estimating a population proportion. And from that, we're going to learn how to actually find what's called a confidence interval. I'll explain what a confidence interval is. But first, let's take a look at the basics. So our goal is, it says, be able to calculate the margin of error. We'll explain what that is, and confidence interval based on a confidence level for a population proportion. We can also do this for a sample for a population mean, but today we're going to focus on population proportion. And to be able to estimate a minimum sample size is needed for a given confidence level. So first, we're going to go through some details, going to go through some discussions, definitions, and kind of explaining things before we get to that. First, what's called a point estimate is a single value used to approximate a population parameter. In this case, we're talking about a population proportion. So once again, maybe the population proportion is maybe the people who's, is your favorite color. That's the question, is your favorite color blue? Okay. What population of the proportion of the population would actually say yes? Okay. Now, we don't know that in reality for sure without asking everyone, which would take a long time, but we can do a sample. And so we could do some sample, maybe of say 1,000 people randomly selected. And then we would ask them that question, is blue your favorite color? And then the yeses would be then our population, our sample proportion. So our population proportion would be P, which would be unknown. We wouldn't know that. But our sample proportion would be P in this little, like a little rooftop on, we'll just call that P hat. And that's what we want to estimate the population with. Now we can also do the same thing, the population mean mu and the sample mean X bar. Okay, but here we're talking about portions. So when estimate the population, the real value with the sample population, we're going to call P hat. So that's our point estimate for it. Of course, the problem, as you can imagine, is we don't know for sure how close that is, how close it is to the actual value. So then we want to create what's called a confidence interval. The confidence interval is a statistical way of trying to measure or get an idea of what the statistical uncertainty is. So let's just read this part. It says a confidence interval is a range of values used to estimate the true value of a population parameter, such as a proportion or mean. It's an interval whose center is a population estimate of the parameter. So just like the center, if we want to estimate a population proportion, P, we're going to estimate that with the population proportion, sample proportion, P hat. Okay. And this is also based on this interval when I have a certain percentage of confidence, based only on the statistical method used to calculate the confidence interval, that the true population proportion parameters are within the confidence interval. So basically, it's a way of saying, it's just based on statistics, how certain are we the actual values within this interval we're creating, okay? This range, higher and lower values. Typical confidence intervals are 90%, 95%, and 99% confidence intervals, okay? So that's what our statistical level of confidence is. The actual value is actually in this interval. So here's an example, and this isn't a real example, but just an example. A recent poll of 1,000 people, and that would also want to be a random poll, say that 52% of the Americans are satisfied with the job the current president is doing. The 95% confidence interval is this, okay? So this would be our population, or sample population, our sample proportion is 52%, 0.52 as a decimal. That's our point estimate. Then our confidence interval would be this, the 95% confidence interval would go from, in terms of decimals, so right in the middle is 0.52, then it goes from 0.49 to 0.55. So what we're saying is, based just on the statistics, on statistical error, we're 95% confident that the real value is actually within from 0.49 to 0.55, okay? So that, or basically 49% to 55%, the real value is somewhere of Americans who are satisfied with the job the current president is doing, based on this example. Now, a couple things to mention. This is just based on this infinite interval, just based on statistical error. There are other kinds of error, other kinds of uncertainty we may not be able to really calculate, but that would actually, if you could calculate, it would actually create a wider interval, give us more uncertainty. And also, the more we increase our confidence levels, the larger our interval will be. Okay, so that's a trade-off. So if you want more confidence, you actually have captured the true value within your interval, then the essentially more uncertainty you have. Now, this confidence level is a probability we're going to call 1 minus alpha. Once again, this is going to be such as 0.95, or for 95%. that the confidence interval actually does contain the population parameter, assuming the estimation process is repeated a large number of times. So it's more based on the method of doing this. But our common ones we're going to use for confidence levels are for 90%, then alpha, 1 minus that, 1 minus 0.9 is 0.1, 95%, then 1 minus 0.95 is our alpha is 0.05, and then for 99% our alpha is 0.01. These alphas then what we use then actually help us create our confidence interval. So these percents here are our confidence levels that we actually have. The true value is actually within our confidence interval, and they're based on these alpha values. Now, let's talk about how to interpret a confidence interval. So let's say we're talking about, you can read all this on your own, but I'll summarize it. Let's say you have a 95% confidence interval. So we have alpha of 0.05, that's our error. We want to be 95% certain that we've actually the true value is actually within this interval we created. Okay. If we do statistically correctly, we can say we're 95% confident the interval actually does contain the true value of the population proportion based on this method. The method is basically creating these confidence intervals, as we explain how to do in a moment. Okay, what we're saying, 95% confidence, is let's look at this graph below. We're saying that basically if we create, on average, we create 20 confidence intervals using this method, 19 of them, that would be 95%. If our actual value is, in this example here, P, which is 0.5, then 19 out of 20 times, or 95% of the time, this interval we created, these intervals we created, will actually contain that value of 0.5. And then 1 out of 20, or about 5% of the time, it won't. And once again, that's based on the method, doing this over and over again. So if they ask the question is, does this particular interval, what's the probability this particular interval does contain the method? Well, that's harder to say because that's actually either it does or it doesn't. But based on this method, do this method over and over again, the method indicates that statistically we should be able to calculate the real value 95% of the time, or 19 out of 20 intervals. Okay, we do on average. Okay, now how we're going to actually create this confidence interval is based on this critical value. So remember, critical value is the number on the borderline separating sample statistics that are likely occur from those that are unlikely. But basically, we're going to take this alpha value we've mentioned, okay, for the most common ones. For 90%, alpha is 0.1 or 10%. 95% alpha is 0.05 or 5%, and for 99% alpha is 0.01 or 1%. So what we're going to do then is we're going to divide that alpha in two, and then we want to basically use that to find these little areas out here in the ends. And essentially, we want to make sure that our value is actually within this middle section. And so the error we have is way out here on both ends. But the main thing you need to know is we're going to essentially take this alpha value, which we'll find, then divide it by 2, and then we're going to find these critical values that determine these cutoffs here. Now, we have a few conditions we have to create a confidence interval for a sample proportion. And we're getting that, we'll do an example here in a moment. But we have to have a simple random sample, and unless it's stated otherwise, we assume that's going to be true. Also, have to meet the conditions for binomial procedure have to be satisfied. Those have been stated before in other videos. But basically, those are 3 conditions. And one, the number of observations is fixed. So that's your sample size. That's fixed ahead of time. The second is that your observation is independent. And although that may not technically, in a very technical sense, be true, we assume that's, since we're talking about such a large population, usually we assume that is also true. Then finally, each observation represents 1 or 2 outcomes, either success or failure. We can define it that way. For example, in the previous examples, if we said, you know, do you approve the job the president's doing? That's either success or failure, yes or no. Or is your favorite color blue or not? That's either success or failure, yes or no. Okay, and then also this one has to be at least 5 successes and 5 failures. So we have to verify this. So n, number n, our sample size, times our sample portion has to be greater than p, and also q, which is 1 minus p, has to be greater than or equal to 5. Both have to be greater than or equal to 5. Now, let's talk about this procedure, and then we'll actually look at our first example in a moment. So first, when we create a confidence interval, I have to find the critical values in the form of confidence levels. So basically, we'll be given with a level problem, the problem will state like you want to find this interval with 95% confidence or 99% confidence, for example. And 3 we mentioned are the most common, 90, 95, and 99%. Okay. They want to find the alpha, which is basically 1 minus this as a decimal. So for 99%, alpha is 0.05. Then we want to find the critical value, this for alpha divided by 2. Okay. So once again, go back to our picture then, we're separating that alpha. So we have 2.5%. So 5% is outside of this range, the kind of yellow range. Then 5% we divided into 2. 2.5% is here and 2.5% is there. Now, the main thing is being able to get the critical values, okay, which there's a method to find that. But here, we're just going to focus on the most common values, which are these, okay? So for 90%, your critical value, your z of alpha over 2 is this, 1.645. For 95%, it's 1.96. And for 99%, it's 2.575. We'll use those values in examples as we need to. So there are methods to find a more general critical value, but those are the main ones we'll use. Now, we also have to find something called the margin of error, and that's the next part of it, and that's how we'll actually find our confidence interval. So this margin of error is called E, and basically it's given by this, where we have this critical value, z of alpha over 2, those numbers we're just talking about in this table, you know which confidence level you use. Then the square root of P and Q. So remember, Q is 1 minus P. P is your sample proportion as a decimal, and Q is 1 minus that, the complement of that, and then N is your sample size. Multiply that together to give us our margin of error, okay? So what we do is we create an interval where our sample proportion is right in the middle. Then to get our interval, we add E, our margin of error, to that P, and that gives us our upper bound of our interval. And then we subtract E from P, gives our lower bound of our interval. Okay, so, and that's our 1 minus alpha confidence interval. Now we've said a lot of words, so let's actually put this in examples, and let's actually do one. Let's take a look at a couple over here. So this is a good example. It says, a poll of 1,200 randomly selected adults, there's a random sample, showed that 87% of them have an email account. Determine if the necessary requirements are satisfied for section 7.1, that do the binomial, those binomial requirements that we mentioned. And then if they are, we want to calculate the margin of error E that corresponds to a 95% confidence interval. We're going to find the margin of error E, then I'm also going to find the confidence interval. Okay. So first, let's take a look at those requirements again. Are the necessary conditions met? We have a simple random sample. And so we assume that, let's say it otherwise, we have one of those. The binomial procedure conditions. Or we call those the binomial conditions. Okay, and remember those are number of observations is fixed, right? We have 1,200 randomly selected adults. We can think of this as being independent, okay? And then also we have either success or failure. So either you answer yes or no, this one, you do or do not have an email account. Those are correct, okay? Now, must be at least 5 successes and 5 failures. And clearly that's going to be true. Okay, because we multiply the sample size N times P. We can do that really quickly. So N times P is equal to 1,200 times 0.87. And let's just find out what that is. And that would be 1,044. Okay, that's bigger than 5. The other one might need a little more space. I think I can squeeze it in. So N times Q, remember Q is 1 minus point that. So 1,200 times 1 minus 0.87 or 0.13. And that's going to be 156 rather, and that's also greater than 5. Both are greater than 5. Okay, and at least 5 successes and 5 failures. Okay, so everything is good. So met the conditions. All right, so now we need to find our critical value. So here we want to have a 95% confidence level. We want to be 95% confident that our interval will actually contain the true value. Remember, this is our sample value. So the question is, what's the true value? The true percent of people have an email account. We want to have be 95% confident that our interval is actually going to contain the real value. Okay, we need to find our critical value. So for 95%, our alpha okay, let me just make a this over here. So our alpha is going to be 0.05 or 95%. Then our z of alpha over 2, look at 95% is 1.96. Okay. Now, I want to find the margin of error E. So let's take a look at our definition. So margin of error E is, once again, z of alpha over 2, our critical value, times the square root of p hat, our sample portion, and it's q hat times its complement, and then over n. And if we plug all these in, we have 1.96 times 0.87 times 0.13. Remember, q hat is 0.13 divided by 1200. Here's where we use a calculator. We use like a scientific or graphing calculator to help you out. All right, so let's put all that together. So give me a moment to type that. So 0.87 times 0.13 divided by 1200. And then that's all the square root of that. And then times 1.96. And that comes out to be, now you have to be careful how you round it off. So this is going to be approximately 0.0, I'm going to go to 3 decimal places, 19. Okay, so that's my margin of error. Okay, that's my E. Now, then my 95% confidence interval is just going to be, so look at our confidence interval. So what we're going to do then is basically need to find our upper bound and lower bound. It doesn't matter which we find first. So our lower bound is going to be our p hat minus E, and that's going to be 0.87 minus 0.019. And that's going to be 0.851. And then our upper bound is going to be the margin of error plus E. So 0.87 plus 0.019. And that's going to be our upper bound. So 0.87 plus 0.019. And that's going to be 0.889. Okay, so actually I do need a little space here. Let's move this down. All right, so our confidence interval, I'll also abbreviate it as CI, or 95% confidence interval, is going to be this interval 0.851 to, we'll write a couple different ways. You can write it as in an equality, as, so we're saying that 0.851 is less than or equal to P, which is less than P, which is equal to, which is less than 0.889. Okay. Or we can write it as an interval from, as it shows here, 0.851 to 0.889. Now, what does all this mean? Let's talk about it. Okay. What this means, to explain what this means, we may not write it down, we'll say it then, is that we're 95% sure, that's the reason we put the P here, not the P hat. We're 95% sure the true population proportion of those with email accounts, that was the question, of those with email accounts is, I'll say, between these values. So 85.1%, just change them to percents, and 88.9%. Okay, we're now to space, but you read that. So let me say that again. So what this means then is I'm 95% confident that the true proportion, the true percentage of those who have email accounts in real population based on this is between 85.1% and 88.9%. Okay. Now, I don't know where it is in there, but I'm 95% confident based on this method of it is in there. All right. A few more things to mention. Let's go back and take a look at our margin of error E. Remember this critical value we started with. Now, if you change your confidence level, here we did 95%, let's say we did 90 or 90%, that's the only thing that would change. And if you look at our critical values, all right, if we went the 90% confidence, this would be a smaller number, so our margin of error would be smaller. If we went with 99% confidence, that Z of alpha over 2 would be larger, and so our margin of error would be larger. So that's, once again, that's the trade-off. So if you want more confidence that you actually have, that the true value is actually within your interval, you have to have a wider interval. Okay, so you have more uncertainty. That's a trade-off. Okay, let's take a look at another example. Let me move it up here. This will work basically the same way. Just another one. Okay, this one says a poll of 2,400 randomly selected adults showed that 1,800 of them have cell phone plans. Determine if the necessary requirements are satisfied for section 7.1, those requirements again. If they are, one calculate the margin of error E that corresponds to a 99% confidence level. Okay, let's look at our conditions again. This time I'm not going to write as much. We'll just say whether they are or not. Okay, so must have a simple random sample. I said randomly selected. We assume that's true. Conditions for a binomial procedure must be satisfied. So once again, let's go back to the previous problem. We wrote those out. We're not going to this time, but also just said binomial conditions. So the conditions are, once again, that number of observations is fixed. Our sample size is fixed. We assume our observations are basically independent, and also that we can think of our outcomes either success or failure. So the question is, either do or don't have a cell phone plan. Okay, so those are met so far. It must be at least 5 successes and 5 failures. We can also check that. Now here, this time is a little bit different. Instead of giving us a proportion, just say 1,800 of them have cell phone plans. So actually, we should find our proportion. Okay, so first, our P hat, our sample proportion, is going to be 1,800 divided by 2,400. And that is going to be 2/3, or should be 60.67. Double check that. So 1,800 divided by 2,400, right? So 0.75, not 2/3, 3/4. So that's going to be 0.75 or 75%. Okay, so let's try that. So N times P hat is going to be 2,400 times 0.75, and that's just going to be 1,800, what we just said, and then, which is greater than 5. And this value is greater than 5, that checks. And then n times q, which is 2400, times 1 minus that, which is 0.25. And that's just going to be 600. And that's also greater than 5. Okay. Right. So all those are met. And also that last condition, this one about verifying this has to do with being able to approximate a binomial distribution as a normal distribution, but they're all met. Okay. Now, critical value. Let's go back and take a look. This time, it's going to just make a division here. This time, our alpha is 0.01. Okay, for a 99% confidence level. Go back and take a look at our table. Okay, and so our critical value, z of alpha over 2 for 99% is 2.575. Okay, oops, and that should be, sorry, I changed this to be 99%. I realized I changed that. Okay, now, once again, same thing, find the margin of error E and the 99% confidence interval. So let's take a look. Once again, our E is z of alpha over 2 times the square root of p hat q hat over n. Plug everything in. So 2.575 times the square root of p hat, which is 0.75, times q, which is 1 minus 0.75, which is 0.25. And then it's all divided by 2400, our sample size. Let's plug this into our calculator. Okay. And then that, let's go to round it off. Can we round it off? Here, I'll, once again, round off the 3 decimal places again. And so that's going to be 0.023. Okay, so that's my margin of error. So then now my 99% confidence interval, once again, we need to find our upper and lower bounds for interval. So the lower bound is going to be our p hat, our population or sample proportion minus E, and that's going to be 0.75 minus 0.023. Can we do that? That's going to be 0.727. And then the upper bound is we're just adding that to the sample proportion. So 0.75 plus 0.023. And that's going to be 0.773. Okay, so actually, yeah, let me move this down again. A little more space. So then our 99% confidence interval, we're saying the true value is somewhere between 0.727 and 0.773, or we can write it an interval as an interval, okay, or 0.727 and 0.773. Okay, so once again, what does this mean? Well, what it means is that we're 99% confident that the true proportion of, look back to details, those who have cell phone plans, so the adults, I'll just say adults, but we'll say those who have cell phone plans or adults with cell phone plans. Is between, and let's make this as a percent, 72.7% and 77.3%. Okay, so based on this, statistically, we're 99% confident that the true proportion of adults with cell phone plans is between 72.7% and 77.3%, with our point estimate, which was our sample portion of points, there's 75% being right in the middle. Okay, now once again, this is also, as I said, only based on statistics. So there's probably could be other reasons for error, other sources of error that we're not accounting for with this, and that effectively would make a larger interval. It'd be more to have that certainty that would make essentially a larger interval. Okay, but based on this, 99% confident, we're sure it's somewhere in this interval. Now, once again, if we use 90%, 95% confidence, we'd have a smaller interval, and 90% confidence is a smaller interval still. So you would have a smaller margin of error in those cases, but you're also decreasing your confidence level. Okay. Now, let's take a look at some other ideas related to confidence intervals. So let's talk now about finding the sample population proportion from the confidence intervals. Let's say you're given a confidence interval such as this, or maybe a statement like this, where it says 99% confident that the true portion of adults with cell phone plans is between 72.7% and 77.3%, but you weren't told what the sample proportion was. Well, the way to find it is basically, it's going to be right in the middle of your interval. And so the way to find it is essentially to do an average. Okay. So you have a confidence interval where A is your lower bound and B is your upper bound. Then P is going to be the average of those two, right in the middle. Okay. And then if you need to find the margin of error, okay, just given this interval, need to find the margin of error, you can do that by then essentially it's going to be half the distance between the middle and either bound. And we find that by doing A. Once again, if A is your lower bound and B is your upper bound, then it's going to be A minus B over 2. And actually, probably better if that was, actually, let me change this. It'd be better if that was B minus A over 2. That way we can avoid having a negative, though the absolute value is going to be the same, B minus A over 2. Okay, don't have a negative number, but it's going to be B minus A over 2. Okay, once again, this is true because the margin of error extends an equal distance above and below sample proportion. Let's look at a few examples like that to get a feel for that. So number one, find the sample proportion and the margin of error of the 95% confidence interval like this. Okay, now here, honestly, the confidence interval, confidence level, is just kind of extra information. We don't actually need that for this. All right. So to find P or P hat, our sample interval, okay, it's going to be, so we just average these two values. So 0.49 plus 0.55 divided by 2. Let's do that. And that we do that is going to be 0.52, 52%. So what that means is that the value right in the middle of this interval is 0.52. And that would be in this interval, that would be our sample proportion. Okay. Now then the margin of error, then we just essentially divide this interval length by 2. And so do B minus A. So the upper bound minus the lower bound. So 0.55 minus 0.49 divided by 2. And let's do that. And that is going to be 0.03. So that's actually our margin of error. So if you wanted to construct this confidence interval the way we did before, then this would be your population proportion. This is the margin of error. And if you did that, if you subtracted 0.03 from 0.52, you get your lower bound, 0.49. If you added 0.03 to 0.52, you get your upper bound, 0.55. Okay. Now, let's do the same thing here. And here, we're actually being stated in a different way. Instead of an interval like this, is giving kind of as inequality, but it works the same idea. Okay. Find the sample portion and the margin of error for the 95% confidence interval here. All right. So in the same way, our P hat is going to be the average of those. So 0.138 plus 0.242 divided by 2. Let's do that on the calculator. that is going to be 0.19. And then E is going to be the upper bound minus the lower bound. So 0.242 minus 0.138. And then that's going to be divided by 2. So our margin of error is 0.052. And you can see if you constructed this confidence interval based on your P and your E, your sample proportion and your margin of error, if you subtracted this E from this number, you get 0.138. You can try this on your own. Then added this to 0.052 to 0.19, you get 0.242. Okay. All right. And then our last topic here is the question of finding the minimal sample size. So often you want to have some idea of what size sample you need, because in real life, conducting a sample can be expensive and time consuming. And ideally, you'd like to have as large a sample as possible, but once again, that's difficult because really large samples, once again, take time and cost money. So you want to get an idea of what's a legitimate sample size you can use to kind of get the confidence level you want with a given margin of error. So let's say you know what margin of error you want, and maybe you want to have a certain predetermined confidence level. So what sample size you need? That's the next idea. So sometimes you know the minimum sample size you must use for a certain level of confidence. And it's given by this formula. And basically this formula is just the formula for the margin of error solved for n. Okay, so we have to, and it says we use given information about P and Q. Now here, of course, the problem is you can imagine in real life, you don't know what P and Q are. That's what you're trying to find. Okay, P, or Q from P. So sometimes now what you can use, maybe there's a previous sample, previous work that's been done using estimated. But also is if we don't know what P or Q are, we're going to use P times Q is 0.25. And that's in real life, that's probably what we have to do more often because you won't know the actual value. Okay, so let's talk about that. So let's do a couple examples. So for 95% confidence interval with E of 4 percentage points and P of 0.35, find the minimal sample size needed. Okay, so first off, our E, 4 percentage points is 4%. So we need to use this as a decimal, so 0.04. Now, and we have 95% confidence. So what we need then, that implies that our Z of alpha over 2, go back to our small table we had, 95% Z of alpha over 2 is 1.96. Okay. Now, if you also notice here, this time we're actually told that P is 0.35. So maybe we got that from some previous work. Okay. So P hat is, or P hat rather, is 0.35. So then Q hat is 1 minus 0.35, which is going to be 0.65. Okay. So let's plug all this in. So N then is going to be Z of alpha over 2 squared. And so that's going to be 1.96 squared times P times Q. So 0.35 times 0.65. This is all divided by E squared. So 0.04 squared. Okay. Now, let's do that. And that is going to be 546 point, I'll do 2.23. And one thing we also want to say here is actually when you're doing these, you always want to round up. because to maintain that confidence interval, we know make sure you need more numbers. Maintain your confidence, you need more than fewer. Okay, so round up. And so n needs to be 547. Okay, need at least that many. That's also this is a minimum sample size. Okay, so if you can go more, that's better, but that's a minimum sample size. Okay, let's do one more. And it looks like we're almost out of space, but that's okay. So number 2, for a 99% confidence interval with E 0.02 and a sample portion of 72%, find the minimum sample size needed. In fact, I'm going to change this. Let's just say we don't know a sample proportion. Okay. Let's just say we want a confidence interval, confidence level. Okay, I'll go move this down the next page or more space. So let's we just know a confidence or know a margin of error and know a confidence level. Find the minimum sample size. Okay, so this time let's say we don't know the proportion. So once again, do the same thing. So our E, this time is given as a decimal, which is good. So 0.02. Okay. Then for 99% confidence, once again, find our Z of alpha over 2. So look back at our table. For 99% confidence is 2.575. I wrote that down. 2.575. Now here, since P is unknown, we're going to use P hat times Q hat is equal to 0.25. It turns out that that's actually, for any P and Q you have, remember Q is 1 minus P, 0.25 is actually the maximum. So that gives you the most confidence. Okay. Now let's plug all these in. And so N is equal to 2.575 squared times 0.25. Substitute that for P times Q over 0.02 squared. Okay, and then we'll plug all that in. And we get 4,144.14. And once again, round up. And so that's going to give us 4,145. So once again, that's our minimum sample size. So both these are minimum. Write that here. So minimum sample size. If you can go a larger sample, that's good, but that's the minimum you'll need for those conditions. Now, on this one, if we had a good idea of what we expect the P to be, for this one, we could have had a larger or smaller sample size. We could better, but since we don't, this is our minimum. So let's talk about what we learned today and summarize. So what we learned is the idea of a point estimate, which is a sample proportion or mean. Learn the confidence interval, so we can statistically find a confidence interval, which will give us basically some confidence level that or the actual values in that interval. And usually we use 90%, 95%, and 99%. And then what our confidence in is based on the method of that percent of the time actually capturing the actual value. Then we learned how to find, of course, the critical value, which will be given. It's easy to find. Most of the time, usually we'll use those 3 values. A way to find basically the margin of error. Oops, that's what happened to that. The margin of error. And from the margin of error, we can create this confidence interval. And then we use that to say basically the result, however confidence level we have, the actual values in that interval. Then we found ways to, if we're given an interval without the margin of error or the sample proportion, you can actually find those values. And then finally, we learned how to find a minimum sample size needed for our conditions. You can also do this same method for estimating population mean, which we'll see in a future video. Thank you. Have a good day.